They rationalized. Okay, so we're going to find the domain of these functions, and remember that when you're finding the domain of a square root, you can take the interior and set it greater than or equal to 0. So 5 minus x greater than or equal to 0, and then if we solve, we could add the x over and solve it that way, or we could subtract the 5 and divide by negative, whichever one makes better sense to you. So if I divide by the negative, it becomes x is less than or equal to positive 5. You can also think of it as the square root of negative x plus 5, or the square root of negative parentheses x minus 5. So it's a square root reflected over and then shifted to the right 5. And so you can see negative infinity up to 5. But you can just use this process and say x has got to be less than or equal to 5, so negative infinity to 5. Number 12, this is a rational expression. So for rational expressions, you're concerned about when the denominator equals 0. So I set the denominator not equal to 0 because that's what I can't have happen. So 2x plus 5 cannot equal 0, which means x cannot equal a negative 5 halves. So my domain is negative infinity to negative 5 halves, and then negative 5 halves to infinity. So everything but negative 5 halves. The next one is a cubic. It's a regular polynomial, and so the domain of that is all real numbers, or negative infinity to positive infinity. Number 14 is a logarithm, and I don't know if you guys remember, but logs can only exist when you take log of a positive number. So we can only take log of positive numbers because exponentials, their inverses, only equal positive numbers. They never become negative. That means log, it's like if that's the range of the original, it's the domain. So that logs only have positive numbers, which means we do the same thing here as we do with the square root. X minus 4 has to be greater than or equal to 0, which means x has to be greater than or equal to 4. So my domain is 4 to infinity. Number 15 is a square root, so very similar to what we did in number 11. I'm going to set the interior greater than or equal to 0, which means x is going to be greater than or equal to negative 10. So my domain is negative 10 to infinity. Number 16 is a rational expression. So we take the denominator and say the denominator cannot equal 0, which means x cannot equal 7, because 7 minus 7 will give me 0. So my domain is negative infinity to 7 and 7 to infinity. 17 is a linear function, and linear is a regular polynomial, so the domain is all real numbers, or negative infinity to positive infinity. And number 18 is a quadratic. It's just a regular quadratic, so the domain is all real numbers, or negative infinity to positive infinity. So now we are going to start doing some composition, or actually not necessarily just composition, but combinations of functions and finding their domains. So the first one says add the functions k and f. So k of x equals this one. So 2 square roots of x plus 10 plus 3 plus f of x, which is the square root of 5 minus x. So this equals this. I cannot combine these two fractions. I mean, I can't, fractions. I can't combine these two functions. Yes, I have two square roots, but they don't have the same radicand, so I can't. I just have to leave them as is. And so then I'm supposed to find the domain. So domain is where they both exist, right? So when I think about k exists from negative 10 until infinity. And f exists only up until positive 5. So they both exist only between the two, which means my answer is this only exists from negative 10 to 5. I'm going to draw that a little bit differently. So k exists from negative 10 on, and f exists up until 5. So they both exist only between negative 10 and 5. Okay, h minus n. So h of x is this cubic function. So x cubed minus 4x plus 1 minus n of x, so minus this right here. Now I'm going to write minus parentheses 3x minus 4, because you got to remember you're subtracting that whole expression. And then I'm going to try and combine like terms at the same time. So I've got x cubed. This is a negative 4x minus a 3x, so minus 7x. This is a 1 minus a negative 4, so plus 4, so plus 5. So that is the sum, or the difference of the two functions, not the sum. And the domain, well, h of x exists everywhere, and n of x exists everywhere, so the difference exists everywhere. And there we go. Alright, let's go to number 21. N is the linear function 3x minus 4. G is the function, okay, so G is a little bit interesting. It's the function x minus 3 over 2x plus 5. So, first off, let's talk about the, like, they can only exist where they both exist, right? G does not exist at negative 5 halves. So negative 5 halves is out. Okay? So let's go ahead and state that. Alright. But now I've got this new expression, and it's a little bit more interesting because when I divide one fraction by another, which is, I can rewrite this whole numerator as something over 1, true? That becomes 3x minus 4 over 1 times the reciprocal 2x plus 5 over x minus 3, right? Well, this right here can be simplified to this fraction. The denominator, you multiply fractions, you multiply straight across, and the numerator is going to be 6x squared plus 15x minus 8x, so plus 7x, and then minus 20. So this is my final answer, but again, the original did not exist at negative 5 halves, so the final cannot. But it also cannot exist at 3, because 3 minus 3 would give me 0. So my domain is everything but those two numbers. So I don't necessarily leave myself in a space, but I'll go ahead and negative infinity to negative 5 halves, negative 5 halves to 3, and 3 to infinity. Okay. Now let's talk about 22. G divided by f. So g is that rational function, so we're going to write that down again. So x minus 3 over 2x plus 5 divided by f of x, which is this square root thing. Okay, so divided by, I should have written that a little bit higher. So let me redo that real quick. I'm going to let this be the center fraction, this fraction right there. My numerator is g, x minus 3 over 2x plus 5, and my denominator is this square root of 5 minus x. Okay, which is technically over 1. So let's just remind ourselves, this one doesn't exist at negative 5 halves, and this one only exists up until 5. So if I imagine my two lines, right? So the first one, negative 5 halves is out. So it's everything but those, or but that number. The second one, it only exists up until 5. So 5 is over here. So when I think about combining the two, first off, if I multiply by the reciprocal, 1 over the square root of 5 minus x, then I end up with x minus 3 over, and then this times this. Now I'm not going to distribute because I can't distribute with the square root, so I'm just going to write this times the square root of 5 minus x. And that is my final expression for the inverse. Or not for the inverse. Oof, for the division. Okay, so normally I would say my answer is going to be negative infinity, negative 5 halves, and then negative 5 halves to 5. But I have one more issue. The square root's in the denominator, which means x can no longer equal 5. Yeah? So that means 5 is now out. So my final answer for my domain is going to be negative infinity until negative 5 halves, and then negative 5 halves until 5, not included. And there we go. Let's talk about 23. So 23 is a composition of functions, p of n. So, alright. So I've got my outer function is this quadratic, and my inner function is this linear. So let's first just talk domain. The first step is to find the domain of the interior function. In the domain of the interior function is all real numbers. So for step 1, all real numbers. For step 2, we need to do the composition. So I'm going to write the exterior function. P, so we've got 2, open parentheses, something plus 3 quantity squared. And then my interior function goes inside there, and that is 3x minus 4. Which means I could rewrite this as 2 times 3x minus 1 quantity squared. Which you could expand, you don't need to. So my final answer is a quadratic. There's no square roots, there's no fractions, there's no rational expressions, so there are no more domain issues. So number 4, the domain is all real numbers or negative infinity to positive infinity. Okay, I'm going to end the video there, and then I'll pick back up with number 24.